This is part 5 of a series on Word2Vec. In this video, we'll learn about hierarchical softmax. Hierarchical softmax is a computationally efficient approximation method used in neural networks to handle the large corpus common in natural language processing tasks. It significantly reduces the computational cost compared to the regular softmax. In the last video, we looked at the Huffman algorithm and how to use it to create a Huffman tree. In this video, we'll explore how to train a skipgram model using hierarchical softmax based on a Huffman tree. Now let's look at a Huffman tree for the words in a vocabulary. Let's say we have a very small corpus of just 5 sentences, as follows. And we create a word vocabulary of size 11 words from the corpus as follows. These numbers are the indexes of the words. It starts from 1. Index 0 is reserved for the pad token, which stands for padding. We do not use the pad token here. It will be used later when dealing with natural language processing tasks. And we generate n-gram sequences of words from the corpus. In this example, the trigrams are used. This is what we used previously when explaining the skipgram model. Using this, we built the following training data set. For training a skipgram model, words can be represented as indices in the vocabulary as follows. The number 8 is the index of the word cat, and the number 1 is the index of the word the. Next, we create a word frequency table from the corpus as follows. These numbers represent the frequency of the words. In this corpus, the word the was used 5 times. And the word cat was used 2 times. We build a Huffman tree based on these word frequencies as follows. This can be easily done using the Huffman algorithm we looked at in the last video. In this tree, each leaf node contains a word and its frequency. Words that appear frequently are placed closer to the root of the tree, and words that appear less frequently are placed deeper in the tree. Since this vocabulary contains 11 unique words, this tree also has 11 leaf nodes, and it has 10 internal nodes. Each internal node is assigned a unique number from 0 to 9. And each left branch is assigned a 0. And each right branch is assigned a 1. The sequence of zeros and ones along the path to the leaf node of a word becomes a unique code for that word. The code for the word room is 001. And the code for the word cat is 0110. This is the Huffman tree for a vocabulary of 11 words. And this is a set of Huffman codes for each word. Next, let's look at a hierarchical softmax based on the Huffman tree. Let's say we have a skipgram model with hierarchical softmax as follows. This model consists of an input layer, a word embedding layer, and an output layer consisting of a Huffman tree. Let the set of trainable parameters of the word embedding layer be W, and the set of trainable parameters of the output layer, i.e. Huffman tree, be H. An example of a Huffman tree of the output layer is as follows, and the Huffman code for each word is as follows. Now let's look at how to train word vectors using hierarchical softmax. Let's input the first training data point into this model. The target word is cat, and the context word is the. And the word indices are 8 and 1, respectively. The word index 8 corresponding to cat is input to the input layer. In the word embedding layer, the embedding vector of cat W8 is selected. Now let's see what happens in the output layer. Each internal node in this tree is assigned a unique ID from 0 to 9. And each internal node has a weight vector H, as shown below. First, we get the Huffman code of the context word the, corresponding to the target word cat. This is 110. That means if we follow the path from the root node to the right, and left, we can find the context word the. The probability of moving right from the root node is 100%. This is the desired probability or true probability. The root node ID is 9. Next, we compute the dot product of the embedding vector W8 of the target word cat and the weight vector H9 of the root node. Then we apply the sigmoid function to the result, where sigma denotes a sigmoid function. This is the predicted probability of moving to the right from the root node. The closer this value is to 1, which is the true probability P, the better. To achieve this, we need to update W8 and H9 via backpropagation. This is the core idea of hierarchical softmax. Binary cross-entropy can be used as a loss function as follows. Since the true probability is 1, the loss function L1 becomes like this. Next, we calculate the probability of moving right from node 8. The loss function L2 is computed in the same way as above using W8 and H8. Finally, we calculate the probability of moving left from node 6. This time, the true probability is 0. That is, since we have to move to the left, the probability of moving to the right is 0. Using W8 and H6, we compute the loss function L3 as follows. Since the true probability is 0, L3 becomes like this. Now that we have computed the loss function, we can update W and H via backpropagation. Calculate the average of the losses obtained above. Then we use gradient descent to update W8, H9, H8, and H6 as follows. Next, let's input the third training data point into this model. The index of the target word is 4, the index of the context word is 8, and the Huffman code is 0110. The context word cat belongs to this leaf node. This time D4, H9, H7, H4, H0 are updated. In this way, we input all the training data points into this model and iteratively update the parameters W and H. This is the training process of this model. Once training is complete, we can obtain an embedding vector for each word. This is the final results from training the model. Next, let's verify the results. Let's see what happens when we feed this test data into the trained model. Let's say the parameters W and H of the trained model are as follows. The size of each parameter is set to 8. The index of the input word walking is 5. Since the root node ID is 9, we calculate the dot product of W5 and H9. And take the sigmoid function, which gives us 0.517. This means that there is a 51.7% chance of moving right from the root node and a 48.3% chance of moving left. Since this probability is greater than 0.5, we move to the right. Next, since this node ID is 8, we calculate the dot product of W5 and H8. And compute the probability of moving to the right, which is 0.014. This is less than 0.5, so we move to the left. Finally, since this node ID is 5, we calculate the dot product of W5 and H5, and compute the probability of moving to the right, which is 0.05. This is also less than 0.5, so we move to the left. Then the word in will be output. This is because the word in appears frequently around the word walking in the corpus. When we input the word walking into this model and calculate the probability that each word in the vocabulary will be output, we get the following results. The word in appears most frequently, followed by is and was. And the sum of these probabilities is 1. This has the same function as a regular softmax. In this video, we looked at hierarchical softmax. In the next video, we'll implement this model in TensorFlow.